All right, let's see, what time is it? All right, it is class time. That means it's quiz time. We don't have many more classes left, do we? Is it May 4th? Is the last day of classes? This, I don't know. This may be our last quiz, or maybe the second to last. I'm not sure. We'll see how it goes. So savor it, just in case. This could be your last organic chemistry quiz ever. It kind of blows your mind, doesn't it? All right. Skylar, can I get you to pass these out, please? All right. Zoomers, just hang out for a bit. Or if you're watching this on video, you may want to fast forward right now because we're taking it, please. Skylar has the quizzes. You can always opt to take the 0.
That is true. Everything's optional.
That's right. It reminds me of a very specific rant / observation I have, but not the time or place for it. All right, guys, let's give it 2 more minutes. Good question. I want to say yes. I'm not positive though. I do remember seeing a stray notebook yesterday. Oh, thank you. In the like the NMR IR little room. I can't remember what color it was offhand, but that may be it. Are you missing yours? Oh, okay. Yeah. Yeah. Take a look up there. That might be. All right, guys, let's go ahead and wrap them up. All right, do I need to come grab anybody's? No. Okay. All right, guys, let's go ahead and keeping on here in chapter 22. We're not quite done with nomenclature yet. We got through several of them the other day. There are a few more. I told you there would be a lot of nomenclature here. And here we're actually about to learn about a new type of compound. Ooh, this is one you haven't seen before. It falls in the carboxylic acid derivative family. And that is called an anhydride. Sometimes referred to as an acid anhydride. We're just going to call it anhydride. All right, so an anhydride basically has a structure similar to this. It's actually got 2 carbonyl groups, and they're linked by an oxygen. Right? And there's actually a couple of different types that you can have depending on whether these R groups are identical or not. Right? So in this case, we're going to assume these are identical R groups. And that's called a symmetrical anhydride. Those R groups can also be different. So we can just sort of signify that with an R prime. Think real hard. What do you think we call that? Asymmetrical? No. What were you thinking? That was cruel. That was a little bit of bait and switch. It's actually not called asymmetrical. It's called mixed. Yeah, I wonder why nobody will trust me. See, I only tend to put the gotcha questions like that on kind of trivial things like this, you know? So, I mean, if I'm really asking you a question about understanding, I'm not going to do that. Mainly, I just do it to try to, get Matt to, catch the bait. And he did. So. Now we have symmetrical and mixed anhydrides. Okay, and as far as nomenclature, it's kind of one of those things. It's pretty easy, but it's hard to explain. All right, it's easiest to show you through examples. All right, so let's take an example of a symmetrical anhydride. Okay, so if you have a symmetrical anhydride, here's what you do. You basically take one part of it, like this. I'm just going to cover this up, and you basically sort of pretend that 1/2 plus the oxygen is an acid. So you basically name it sort of as a carboxylic acid. Okay, so if I just covered up this part, pretended we had an O here, what would the name of that be as an acid? What was that? You had to go look. Yeah. It was in there though? Good. What would that acid be called if it was an acid? What would a 2-carbon carboxylic acid be called? We're going to go IUPAC name too. Common name would be acetic acid. But ethanoic acid, right? All right. Now, it's not an acid, it's an anhydride. So what you do is replace the word acid with anhydride. Pretty simple. So not ethanoic acid, this is going to be ethanoic anhydride. Another symmetrical anhydride. In this case, both sides are 4 carbons. So what would this one be called? Butanoic anhydride. Yeah. Pretty simple. Nothing more to it than that. Okay. Now for mixed anhydrates, it's a little bit more complicated. Not too bad, but still a little bit more complicated because you have 2 different R groups, right? So we can't just say, well, one blanket term is going to cover them. All right, so let's say we had something like this. Okay. Now in this case, each R group is definitely different, right? We have different carbon chain lengths. So what you have to do here, for lack of a better phrasing, name each side as an acid, and then alphabetize. And just like last time, replace the word acid with anhydride. Okay. So here's what we're going to do. All right, let's just cover up this part right over here and just work with this side, right? If this was an acid, what would it be called? That's a 3-carbon acid. That would be propanoic acid. All right, so keep that in mind. Now we're going to do the same thing, but for the other side. That's pentanoic, right? Because that's a 5-carbon unit. So what we're going to do is we're going to take those 2 descriptors, write them down, and alphabetize them. So we're going to have pentanoic, propanoic, and instead of writing the word acid, we have anhydride. So this is pentanoic, propanoic, anhydride. So not hard, but a quirky little system. Definitely a little bit different than some of the other ones we've got. All right. Any questions about anhydrides? All right. Rolling right along. Let's talk about amides. Right. And if y'all remember, we've talked about amides a few times here and there, especially when talking about IR spectra. And you know, there's actually 3 different types of amides. There's primary, secondary, and tertiary. So let's look at primary amides first. Right. Remember, primary amides, they've always got this general structure. They always have an NH2 group attached to their carbonyl, and then some sort of R group. All right, so here's the steps. Number 1, name as an acid. And that applies to both cyclic and acyclic. Right? Then you're going to replace the ic acid part of it. If it's acyclic, or the ilic acid part, if it's cyclic, with the word amide. Well, I kind of all squished that into one thing, so I guess I don't really need the one over here. All right, so let's take a look. All right, let's see if we can name this particular amide. All right, so the first thing we're going to do is we're going to name our parent chain as an acid. All right, so if this was an acid, what would our parent acid name be? What's that? Pentanoic acid, all right? Now that's an acyclic amide. So we're going to go up here. We're going to replace that ic acid with the word amide. Ooh, I made a mistake. Adjust this. This should be oic acid instead of ic acid. That'll change things. Couldn't read my own writing. So we replace the oic acid with the word amide. So the parent for this one is actually pentanamide. Pentanamide. Just like with any of the other acid derivatives, you're always going to number this carbon as number 1. All right. And we have a methyl group coming off of number 3. So that is 3-methyl-pentanamide. Yeah. So make sense? Any questions? All right, let's try a cyclic one. Remember, cyclics have those weird other rules in them. Can I erase this? All right, so the rules are the same at the beginning. Go ahead and name this as if it were a cyclic acid. What would the name of this be if this was an acid? Very good. Cyclohexane, carboxylic. It's kind of funny how that's all one word, but it is. Acid. Right. Now, since this is a cyclic amide, we're actually not going to replace oic acid because there's not an oic acid. We're going to replace the ilic acid part of this. And voila, that becomes cyclohexane carboxamide. Not too bad. All right. Any questions so far? Now, when we get to secondary and tertiary amides here in a second, that's where you're going to see some changes. Not necessarily changes to this process, but sort of additions to that process. All right. So let's take a look at secondary amides. Now, the thing about secondary amides is they're going to have an extra R group attached to your nitrogen. And that's actually the first thing that we have to do here is we have to identify what the R group is, and we have to tell you, the audience, that it's located on the nitrogen. So here's how we do it. First thing you do is you name the R group on the nitrogen. You're going to label it as capital N dash, and then whatever alkyl group it is. So you could have N-methyl, N-propyl, N-sec-butyl, et cetera, just depending on what the R group is. And you have to label it with the prefix N to tell the reader that, hey, this butyl group is on the nitrogen. And from there on out, you just follow the same rules that we learned for primary amides. Take a look at this guy right here. This is a good example of a secondary amide. All right. So according to our process here, what's the first thing we want to write down? What's that, Marissa? N-isopropyl. Yeah, you see on the nitrogen, you have an isopropyl group. So that's going to be N-isopropyl. And the rest of this, like I said, you can just treat as primary. All right. So what's the parent amide name going to be here? hexanoic acid, which becomes hexanamide. Very good. And just like before, our carboxyl carbon gets number 1. And we have a substituent at number 4, that's a bromo. So N-isopropyl 4-bromo. The N, no matter what, should come first when you write this. So you can ignore the alphabetical order here. The N part gets to go first as you write the name. Okay. Does that make sense? Any questions about secondary notes? All right. And then we got tertiaries. All right, tertiaries are going to have a nitrogen that has 2 R groups on it. So something like that. All right. And as you might suspect, we got to account for both of those R groups. All right. So you actually have a couple of different situations here. All right. So let me write this down first. First thing you do is got to name both R groups. All right. You have a couple of different situations. It's possible those 2 R groups on the nitrogen could be exactly the same, right? You might have 2 methyl groups on nitrogen, 2 ethyl groups, whatever. All right. So if that's the case, what you do is you write N, comma N, dialkyl. So if you have 2 methyl groups, it would be N, comma N, dimethyl. You have to write the N twice. All right. The other possibility is that the R groups would be different. You might have 1 methyl and 1 ethyl, for example. In that case, you write N-alkyl for 1, and another N-alkyl for the other one in alphabetical order. So if you had a methyl and an ethyl, you would label it as N-ethyl, N-methyl, blah, 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 blah. And then from there on out, again, you just follow the same rules for primary amines. Okay. All right, let's take a look at a couple of examples. All right, how would we name that? Start off with the alpha groups. You have 2 different ones, right? Methyl and a propyl. So you want to count for both of those. Methyl comes before propyl, so that would be N-methyl dash N-propyl. Yep. And then all you have to do is put in the parent name of the emitter. Butanate. Very good. N-methyl N-propyl butanate. Get creative with this one. One looks a little scary. All right, we got nitrogen, we have identical R groups. What are we going to do as far as the name? What's that? N, comma, N, di, tert, butyl. We have two tert butyl groups, identical on the nitrogen, so we have to have two N's in di-tert butyl. And then we're going to put the rest of our name here. I'm probably going to have to go down here because I'm running out of board space. What's the parent name of this mid? Very good. Cyclobutane carboxamide. All right. Any questions on nomenclature of amides? All right, we got one more compound to learn nomenclature of, and then we'll be done. This will be our last nomenclature of the year. Oh, see, we're gonna have all these milestone moments. Treasure them. I tend to think that you might be a little bit jaded and non-sentimental about this, but you know, maybe. All right. This is going to be what may be another new group of compounds where you can't remember if I've discussed these or not before. These are called nitriles. You've probably heard the term nitrile before, have you? If you have, where have you heard it? Gloves, yeah, you got all one of the nitrile gloves. Those are actually polymers. They're polymeric nitriles made out of a monomer that contains nitrile groups. Basically, a nitrile is going to be something that has a carbon-nitrogen triple bond. And you can see, you know, if we think of all the other ones like esters and acids and acid chlorides and all this, if we sort of think of those as being sister compounds, this is like the weird cousin of the carboxylic acid or the carboxylic acid derivatives. It doesn't have a carbonyl, but just like all the other ones, it's got a carbon with 3 bonds to electronegative atoms. So it's kind of in the same family. All right. So the name nitriles. First, find the longest carbon chain with your nitrile group. Number to give this carbon right here, number 1. All right, and what you're going to do is actually, you're going to name it as an alkane. And you're not going to erase anything from the alkane name. You're just going to then simply add the word nitrile to the end of it. So there's an example of a nitrile. What would the parent name of this be? What's that? Hexane? Yep. And how do we modify it? Add nitrile. Boom. So instead of hexane, this is hexane nitrile, all one word. Right? By definition, the carbon of your CN group is going to be number 1. And it looks like we have chlorines at 2 and 4. That'll be 2, 4 dichloro. 2,4-dichlorohexane nitrile. Okay. Any questions so far? Okay. Now you can also sort of treat CN groups as substituents. Like they can be hanging off of other larger chains and rings and stuff. It's kind of like, you know, alcohol groups, OHs. Sometimes we treat the OH as a substituent, and we call it a hydroxy group. When it's a substituent, we call it a cyano group. So for example, say we had something like that, right? If we have it hanging off of a benzene ring, this would be called cyanobenzene. All right. That is basically it for all this nomenclature. Whew. The biggest chunk of the year, but what better time to put the biggest chunk of nomenclature than the very end? Are there any questions about nitriles or any of the other species? All right. Are you hoping I put lots of nomenclature? Actually, never mind. You won't see this nomenclature until the final exam. So never mind. I was about to say, do you want me to just put lots and lots of nomenclature on the next test? But still, the answer is still yes, right? Keep that in mind. All right, we had a little bit of time here. Let's just kind of go ahead and get our feet wet a little bit into the reaction chemistry. All right, now, again, if you think back to chapter 20, right, we learned some reactions of both aldehydes and ketones, and then we also learned some reactions of acid derivatives, right, using hydride reductions and organometallics. Again, we had 2 very broad categories. We saw that aldehydes and ketones underwent nucleophilic addition. And what did the acids and acid derivatives do? What types of reactions did they undergo? Oh Lord, we may be in trouble. Well, if you think of the big 3, addition, substitution, and elimination, the aldehydes and ketones underwent addition. So it's probably not that one. What did which of the other 2 did acid derivatives undergo? Substitutions, yeah. So it stands to reason that we're probably going to be looking at some nucleophilic substitutions. And we are. That's exactly what's going to happen. The principle is just like the last time, right? We're going to have better leaving groups than we could possibly have in aldehydes or ketones. Right? So the principles are largely the same. The big difference is we're going to be using different types of nucleophiles than we did in chapter 20. And as you'll see, in certain cases, we have to get a little bit creative. right? The big thing about these is that when you look at the reactions of all these compounds, for almost all of them, they involve turning one type of acid derivative into another one. So we can turn acid chlorides into esters. We can turn carboxylic acids into amides, et cetera, et cetera. So we're going to be learning how to do that, all right? And the most versatile of all these is going to be the acid chlorides. And that's not surprising. We saw this before as well. What do you think the leaving group in an acid chloride is going to be? Cl minus, which we know is a really, really good leaving group. It leaves very, very easily. So it's very easy to displace that. For that reason, acid chlorides are exceptionally reactive species. For practical purposes, sometimes they're even too reactive. Like, you know, for example, in polymer manufacturing, you can make polyesters from acid chlorides, but a lot of times that's not a favored technique. Number one, because acid chlorides are really, really bad for the environment. And also number two, they're so reactive, their reactions are a little bit hard to control sometimes. Right? But they're also the most versatile. You can do the most stuff with them. All right? So we're going to see several reactions of acid chlorides. All right? I'm going to show you one real quick. And that's reaction with a carboxylate ion. A carboxylate ion is just a deprotonated carboxylic acid. So let's say you had this. Okay, that's an example of a carboxylate ion. Let's see if we can predict the mechanism of this. No joke, it's going to be very, very straightforward. What do you think is going to happen here? The O minus is going to attack the carbonyl carbon, and the Cl minus is going to leave. Exactly. And that's it. That's literally all that happens. Isn't that an awesome mechanism? Quick and easy. But you'll see we made another type of acid derivative here. What type of material did we make? What has the carbonyl, oxygen, carbonyl? That is an anhydride. Yep. So if you react an acid chloride with a carboxylate, you can make an anhydride. So again, you can sort of program this, right? You know, you can have different types of carboxylate groups, just depending on what acid you started off with and deprotonate it. Okay. That's literally it for that reaction. Very, very simple. And it's a good one to start off with and end the day with as well. All right. Any questions about anything we talked about? All right, guys. Have a good weekend.